Alright, so this first section is an intro to matrices and systems of linear equations. So basically it's a nice little summary of what we're going to be doing the entire semester in linear algebra. All we're really going to be doing is solving for linear equations. You may think that's not that bad, did this in high school and so forth, even in college when it came to partially that kind of stuff. And you're correct. But we're getting a little more complex because now we're just not one variable or two variables, multiple variables. Okay, so for our case, we're going to learn how to solve for things like this, where we have x1, x2, and x3, or nth variables themselves. Okay, so how that's going to work is, there we go, I'm just trying to get my pen ready. So in general, a general linear equation, we say, it looks like this. Okay. Now again, you may be wondering why this is called linear, and the whole reason why it's called linear is because it doesn't have powers. That's literally it. So we know a linear equation being like this, but if it does have a power, it's still technically called a linear equation. Okay, so kind of fun, interesting aspect there. Okay. So we already know how to solve for linear equations. You may be wondering, like, well, that's not that bad. This whole class isn't going to be that bad when it comes to solving. Yes and no, right? So there's multiple ways to do it. There's graphing, elimination, substitution, all that fun stuff. Kramer's rule as well. We'll talk about that more way back in this as well. But what we're going to be talking about the most is matrix representation, which you may or may not have seen in college algebra or in your algebra 2 classes in high school. Okay? So what we're going to be doing is solving for things like this, using matrix representation. Okay? But before we get there, we want to show how to actually create a matrix representation. Okay? And the first step is showing how many rows and columns we're actually going to have. Okay? Now, the number of rows and columns depends on the number of variables and the number of equations we actually have. Okay? So, for example, the above portion is called a 2 by 3 system. Okay? The reason why it's called a 2 by 3 system because it has 2 rows and 3 columns. Okay. So what that means is the number of rows represents the number of equations we have, and then the number of columns tells me how many variables we actually have. Okay. So if you have a 5 by 4 system, that's saying you have 5 equations and 4 different variables. Okay. And that's always going to be the system, how it goes. Okay. So rows always comes first, so the number of equations always comes first, then the actual number of variables. Okay. So in general, if we have an n by n matrix or n by m system, it's going to look like this. Like that. So hence we will have an n by n system of equations. Okay, so this is a general term, so we won't get too broad in the aspect, but that's how it's going to look like. So going back to multivariable, right? What does this actually look like? Okay, so remember we're solving for systems. So in 2 dimension we had 3 different answers, right? We could have had the parallel answer, which means there's no solution. Right, if the systems are just parallel to each other, so we have no solution, which technically is going to be possible in our case. And then after that, we had infinite many solutions, means they were both on the same line. And then the third one is we actually have a solution, right, meaning they cross somewhere. Okay. Well, we have the same process when it comes to 3 dimensions and so forth, right? Because this is just 3 variables, but we can actually have nth variables, right? So, but we're just going to stick with 3D for now. So the equivalent of parallel lines in 3 dimensions is the planes are parallel. The equivalent of this happening would be the planes intersect through each other. And then the last one is they all intersect either at a line or at one point as possibly you can. Mostly it's going to be a line. So let's see if I could do my best to do this. So it looks something like that. So now the question is, how do we represent it, right? So basically, most of our situations are going to be one of these three. Preferably, basically, these two here. And you'll see what that means in a little bit. But how do we actually do a matrix representation? Okay. All right. So matrix representation of a system. So every system of equations get represented as a matrix. So this will give us a 2x2 matrix here. So how this is going to work is we're going to have a matrix, and depending on the person, you can either put it like in little brackets, or you can just have it like this. Just a textbook has like this, so I'm just going to treat it just like that. But you could put it like this as well. So how this works out is the matrix always has just coefficients, meaning numbers. Okay? And how this works is all the x variables coefficients go here, and all the x2 coefficients go there. Okay? So for example, the number in front of x1 is 3, so you put the 3 here. Number in front of here is -5, so you keep the sign. And now you do the same thing for the second one. So number in front of x1 is 1, number in front of this one is going to be 3. And that's it. That's how we make it a matrix. So this is called the coefficient matrix. Now, that's what is the coefficient, but we want more in depth. So we're going to something called the augmented matrix, which we're going to be using much more itself. Okay. Now, when it comes to the augmented matrix, you're going to add one extra column to it, and that column is going to be the actual values they're equal to. So it's the same coefficient matrix. Now this is where your textbook and me are going to change a little bit. In your textbook, they don't do this, what we're about to do, they just brought it up. So in your textbook, you're going to see it this way as your augmented matrix. Okay. How I was used to look at this situation is this equal sign here represents this line there. So you can know that these represent the x's, and this represents the actual answers, b's. So if we go back over here, you can now tell where the A1s and A's and the B1s represent, and this equal sign represents the line itself. Now, you don't have to do that, but just for my sake, I always do just to tell myself that these are the actual answers themselves, not an additional variable alongside of it. Okay, but this is what's called the augmented matrix, what we care about the most. Okay. So why don't we just do a little example just doing that kind of stuff here. So we could create both the coefficient and the augmented matrix for the system here. Now, one thing you got to be careful of is, remember, these are all x's. So because we have 1, 2, 3 variables, 3 different columns. So bringing down, so it'll be, first one here will be 1, 4, -7, -5, 7, -1, 2, 1, and then 2. So for our coefficient matrix, this is a 3 by 3. 3 rows, 3 columns. However, notice our technical one, we have 1, 2, 3, 3 by 3 matrix. So this is our coefficient. Now we go to our augmented matrix, which is the same thing, just with the extra column. and then we just put the numbers. Okay. And there we go. Coefficient, augmented matrix. Now, the question now becomes, what can we do with these? More precisely, our augmented matrix. Okay? So we have three special rules we could do for matrices, or according to our augmented matrix. These three rules are: I can interchange any two rows, I can multiply a row by a non-zero scalar, and the third one is I can add a constant multiple of one to another. Okay? So I'm going to give you an example of each. Okay? So we're going to start with this matrix. Okay. So let's do number one. So I can interchange any two rows. So I could pick any two rows I want. My rows go this way. Right? So I'm going to interchange row 1 with row 2. So I'm just going to swap their order. And notice now row 3 is the same. So I'm just going to rewrite 3 the same because that hasn't changed. And I'm just going to swap them. So literally just move them around. So now row 1 is now 3, 1, 2. And row 2 is 2, 0, 5. That's what number 1 says. Again, only 2 at a time. Okay. Now we go on to number 2. 2 says I can multiply any row by a non-scalar. Okay. So again, if I just go back to our example before, okay. And now I can multiply any row I want by a number that's non-zero. So 1/2, 5, 4, anything like that. So I'm going to multiply -2 by row 1. Everything else is the same. And now I just multiply row 1 by -2, so it becomes -4, 0, -20. Oh, sorry, by 2. -10. Now the third one is going to be the interesting one because we're going to be using this one a lot. Add a constant multiple of one row to another. Okay. Now what that really represents is basically I can add any two rows together, and the result is going to be in that row. Okay. So this could be a little confusing at first. Okay. So what this means is, okay, I'm going to now add row 1 plus row 2 together. So I'm just going to straight out add them together. Okay. And now you have a choice. You could put that result either in the first row or the second row, and everything else will stay the same. Okay. So what I'm going to do is I'm going to keep row 2 the same, meaning the result is going to be row 1. So I did nothing in row 3, so I'm just going to copy that down. Okay. I'm keeping row 2, so I'm also going to copy that down. And the result of this addition will now be in row 1. Okay. So 2 plus 3 is 5, 0 plus 1 is 1, and 5 plus 2 is 7, just like that. And again, you could have kept row 1 the same and the result in row 2. So no matter what, noticing you're only changing one row at a time, except for this one. Well, not even changing, you're flipping around, right? But this one, same process. Once you get more comfortable, you could do two things at once. Like for example here, you could have just, instead of this way, you could also done 3 times row 3, right? But that's if you get more comfortable as this goes around, and you could do two things at once. Right? But most of the time, and a lot of the work is, especially in your textbook, you'll see they go step by step by step, and sometimes questions become pretty long. So it takes forever. So an example in your textbook probably would take a whole page to do, because they're just taking their, they're going step by step by step by step, as you'll see in a little bit. Okay, so let's actually try solving for one. Okay? So we're going to do two different ways, just so you can see how the answer is going to be in this case. Okay? So we're going to use elimination and matrix using our 3 rules. Okay? But for now, we'll just use our basic elimination process. So something we all know how to do, or just a little refresher anyways. Okay? So remember, according to the elimination method, you want to pick a variable you want to eliminate, and the nice thing is probably x1 will be easiest to deal with. And I know what you guys probably would want to do is you guys probably want to change these to x, y, z. Yes and no. You could do this, just be careful. Your textbook uses x1, x2, x3 to infinity because it shows that it's one single variable. If you use x, y, z, you're going to x, y, z, w, x, you get rid of letters. But, just in itself, I'm going to be consistent with the textbook itself. But technically, if you want, you can use x, y, z. We'll usually be only using 3 variables anyways, because it's still technically XYZ plane, so it's, graph it in 3 dimensionals. But, each their own, right, at this point. I wouldn't be too particular on the test or exam that you do that. Just be careful you just don't try to graph that, because that'd be tricky to do. Okay, so let's do this. So that means you're just going to subtract down. This gives me 3, and this is 9. So therefore, x2 is going to be 3. And then you're just going to plug it back in, right? So plug x2 into here, subtract it over. So x1 is 2. Wasn't too bad, right, when it comes to elimination method. So we should get the same results using matrix representation. That's the key thing, okay? So let's see if we do. So first off, convert it to our augmented matrix. There we go. Okay. All right, so we're going to use our 3 rules to somehow get 2 and 3 down. Okay. Now, this is the one thing they don't really tell you in the textbook for a while, but our goal after all of this process is to have this. And you'll see why they don't tell you in a little bit, but this is what we want. So, because we know our answers, this is our goal. Okay. But in general, we want this, where B1 and B2 are going to be our answers. That's how we use a matrix representation to get our answers here. Okay? And we'll talk about why this is important in a little bit, why this is so particular. Okay? But for now, we'll just say that's our goal. Okay? All right. Now, the best part is when it comes to matrix representation and solving for a system of using matrices, it is literally the elimination process. So, for example, we wanted to get rid of the x1s, and all we did was add straight down, right? So what does that look like in matrix? We're just going to add the 2 together. So we're going to add row 1 plus row 2, just like we basically did here. Now the problem is we can only change 1 row at a time. So now it's our job. Again, you get to pick now. Do you want the result of this addition to be in row 1? Or do you want the result to be in row 2? It really doesn't matter, right? So I'll be consistent as I'll keep row 1 the same. And now I will change row 2. So the answer of this addition will be now in row 2. So let's see what we get. So it should be exactly what we have here. 0, 3, and 9. Right, when you add them, get it. Check. Look what we got there. Okay, so next up, what do? Well, we divided by 3 to get the answer. Well, guess what? That's exactly what I'm going to do. I'm going to multiply row 2 by 1/3. And remember, it's a fraction. It's a non-zero, so we can technically do that. So now I get that because that has staying the same. Okay, and then when I divide by 3, 0, 1, and then 3. Look at that. That's what we have. And I'll also talk about what that means in a little bit. Okay, so we're halfway through our goal. We got the bottom now. Now we need the top. Okay, so we need now this position to be a 0. Okay, so somehow this needs to be a 0. So basically you're just starting from scratch. Now I want to eliminate the x2s. That's how this process comes into play. All it is elimination method over and over and over and over again. So once we're done with one variable, we go back and just do the same thing for the other variable. We can't plug it back in and all that fun stuff like we did here, like the shortcut. Okay? So now becomes the situation. Well, how do I do elimination method? Well, unlike here where it was already done, where one had positive, one had negative. Normally, if this was like a both negative, we would have multiply 1 by -1, or if this is a 2 and a 1, multiply by -2, right? They get the same values, and then subtract, and then add down. Same thing applies here, right? So these are the same number already, but they have to have opposite sign before to get rid of it. So what I'm going to do is I'm going to multiply. So I'm going to multiply row 1. Actually, multiply row 2. Multiply row 2. Or, you know what? I'll just do it this way. It's probably easier if I do it this way. I'm going to do row 1 minus row 2. There we go. That's probably the best thing to do. Now, the result I'm going to put in row 1. Because I don't want to change row 2. I already got my goal, right? I don't want to change something I already have. I want. So now I just got to remember I'm doing this minus this. So 1 minus 0, 1. 1 minus 1, 0. 5 minus 3, 2. And look at that. We got our goal. Now I'd be wondering, how do we know this is our goal? Remember, this is x1, x2, and this is the b's. So what this is saying is the first row is 1x1 plus 0x2 equals 2. Second row says 0x1 plus 1x2 equals 3. Well, doesn't that say x1 equals 2, x2 equals 3? And there we go. So again, this is going to be our goal when it comes to solving. I'm not sure why your textbook doesn't tell you that to begin with. Why this is important. It's called the identity matrix. We'll talk about that later on. But that's our goal we're going to deal with. Okay? Now, technically, it kind of gives you a hint right here for this definition, but doesn't explicitly tell you. It says two systems of linear equations are equivalent if they have the same set of solutions. In layman's terms, what they're saying is this augmented matrix is equivalent to this one. So this is what it means by the equivalency in matrix format. Now, if you're wondering, how does that make any sense? Well, I can manipulate this matrix to make it look like that, right? The same thing as if you want to do a scalar multiple, right? Technically, these fractions are not the same, right? 4/8 and 1/2, but these are equivalent fractions because one can be simplified to the other. That's what this represents. Okay. So now let's do a little bit more difficult, actually a lot more difficult example. Let's now try solving a 3x3 matrix, which is a little tougher to deal with. Okay. All right, so first off, we're going to convert it to our augmented matrix. Now, this is got to be careful because notice in the first equation, there is no x1, but we have to represent it in the augmented matrix. So we have 0 x1s, 2, 1, and the answer of -2. Okay? So think of like synthetic division. It always has to be applied. So this is technically looking like that. There. Okay, so 3, 5, -5, 1, 2, 4, -2, and then 2. Okay, so now goes back to the same process. I want to use somehow elimination to get rid of some of these variables to begin with. Okay, now just like we set up our goal up here. Okay, a goal for a 3x3 is the same process. We want to eventually look like this. Just like that. Okay. It follows the same process as this, if you noticed. Just we want an extra variable. Okay. Okay, so this part is you gotta figure, okay, how do I get rid of some stuff to do what I want, right? Okay, so let's see. Well, it looks like everything on the bottom is a multiple of 2. So maybe I can first multiply by 1/2 to row 3, just to make it a little simpler for simplification itself. So everything else will stay the same. Now, the best part about matrix representation and this process of solving for a system using matrices is there is no good first step. There's multiple ways to start from here to here. And remember, it's pure algebra, right? Whenever there's a proof for pre-algebra, there's many ways to start. This so you don't have to follow this process here. So this gives me, so if I divide everything by 2 in row 3, I get 1, 2, -1, and then 1. Okay, remember, notice my goal is this. And remember, I can swap rows, right, if I want. And then notice, look at that. I have that 1 there. Maybe if I want to change that position, I can move it around. So why don't we just do that for now? So I'm going to now replace row 1 and row 3. Okay, so it looks like I have this 1 here, which is what I want. Check, check. So somehow I want to get rid of these 0, right? Make these zeros and all that fun stuff. But the goal is, and I'm going to tell you guys now because it's going to be it's a lot difficult as we go along, is just you follow one column at a time. So in other words, I want to match the first column to look like that first. And then I just slowly go down. Don't try to do everything at once. So I'm just going to look at this first column and show that I want it to look like this. And notice I'm already halfway done, or 2/3 of the way done. I got a 1 and a 0, which means now I just got to make this a 0 as well. But again, it goes back to elimination. So how do I eliminate this 3? Well, I can only add or subtract, right? But these are not the same numbers because that won't give me 0. So it looks like, just like if I were to try to get rid of this 1 here, I'm first going to multiply this by -3, or 3 itself, and then subtract it from row 2. So I'm going to do multiply 3 by row 1 minus row 2. Okay. Now, what does that do? So, again, I'm going to multiply row 1 by 3 first, and then subtract it to row 2. Now, the question is, where am I going to put the answer? Row 3 stays the same because I'm not doing anything to it. Okay. Now, think about it. I want this to be a 0, so I want to change the row 2, which means row 1 is the one I want to keep the same.
Students, you should be wrapping up this.
So, how is that going to work? All right, so let's go back here. I'm going to multiply this by 3, so this is now becoming 3, a 6, a -3, 3. And now I'm going to add this by the second row, or subtract it, sorry. So 3 minus 3, 0. 6 minus 5, 1. -3, now this is got to be careful. -3 minus a -5, so that means -3 plus 5 gives you 2. And then 3 minus 1, 2. So notice I got my first column there. Check. Perfect. Okay. So now I'm going to go to the next one. Okay. And the best part is, notice I got a 3rd there. I got my 1 right here. Perfect. Nice, right? Okay, so off this 1, I need a 0 above and a 0 below. So I need a 0 above and a 0 below to get rid of it. Okay, all right, so let's see what we can do now. Okay, well, if you notice, that's kind of nice, right? We already have the 2's there, kind of like we had the 1's earlier, right, up above here. The only difference is 1's positive, 2's positive, 2's positive. So what do? We just subtracted. So that's exactly what we're going to be doing. We're going to do row 1 minus row 3. Now again, the question is, where is the results going to be? Okay, row 2 is going to be the same, right? So I'm just going to copy row 2 down because I don't want to confuse myself. I want to get rid of this, so I'm going to keep row 3. So now, when I subtract row 1 minus row 3, I do 1 minus 0, 1. Notice it still stays the same. 2 minus 2, 0. Now, negative 1 minus 1, negative 2. 1 minus negative 2, so that's 1 plus 2, gives you 3. And there we are. Okay, so we're on the right track now, right? So it's a longer process, but eventually, trust me, if you ever do a 4x4, 5x5, you really don't want to do elimination method. This process actually gets a little easier as we go along. Okay? But we got our 0. So now we got one more 0. We need this to be a 0 as well. Okay? So let's see. We're going to use our pivot point, or we're going to use our 1 to help ourselves out. And we do the same thing we did above when it comes to this subtraction stuff. Okay? So I need it to be the same but opposite. So I'm going to multiply row 2 by 2. That way they're the same number as if they were here. And I'm just going to subtract row 3. So again, it's the same process we did over here. Right, instead of multiplying 3 now, I'm going to multiply by 2 and then subtract it. Row 1 stays the same. Now again, I got to remember, okay, what do I actually changing? Am I changing row 2 or row 3? I want this the same. I don't want that keeps on, so that means I'm staying with row 2, and the result is going to be row 3. Okay, so if I multiply this by 2, just for my little sake, I'll just put it on top of here. So 2, 2, 4, 4. That's the result of multiplying this whole row by 2. And now I'm just going to subtract down. So 0 minus 0, 0. 2 minus 2, 0. 4 minus 1 is 3. And then, now be careful, 4 minus negative 2. So that's 4 plus 2 gives you 6. And now we are 2/3 done. Check. Check. Okay. Now you may think, oh, there's no 1s here. That's not good. But I can make that a 1, right? Remember, I can multiply any row I want by a non-zero scalar. So to make that a 1, I'm just going to divide by 3 to row 3. And everything else is going to be the same. So divide by 3, 0, divide by 3, 0, divide by 3, 1, divide by 3, 2. And look at that. We got our answer for x3. Okay, we're almost done. Now we just got to repeat it one more time to make these zeros. Okay? And we're going to use our pivot point to help ourselves out. So let's start from the top. So this is a negative 2. So it looks like I didn't multiply row 3 by 2. And all I have to do is add it to row 1 because they're already opposite sign. So everything else stays the same. So I'm going to multiply row 3 by 2, so it'll be 0, 0, 2, and 4. And I'm going to add it to row 1. So 0 plus 1 is still 1. 0 plus 0 is 0. Notice that doesn't change, right? That's the best part. 2 minus 2 is 0. And then 4 plus 3 is 7. Look at that. we now have B1. All right, so it looks like all we have to do is one more step, and we got our answer here. So I'm going to do the same thing we did over here. This time, I'm going to multiply -2 to row 3, and then add it to row 2. So it'll be 0, 0, -2, -4, right? I'm multiplying -2 times row 3. Okay, 0 plus 0, 0. 1 plus 0, 1. 2 minus 2, 0. 2 minus 4, -2. And look at that. We're done. We got a result. So remember what this is saying is, this is x1, x2, x3. So this is saying x1 equals 7, x2 equals -2, and x3 equals 2 in this system. There we go. So I just have extra space here just in case you needed more space to do this process. So that's why if there's a bunch of space there. But the last corollary in this section just goes exactly what we did about augmented matrix. So how we do augmented matrix, it looks like this. Is the matrix A, which is the coefficient, and then B is going to be the answers. Now notice why they have the line there. That's kind of why I always represented the line there as an augmented matrix, to show you that this is the coefficient and this is the answers, or the fully augmented matrix. Okay? So suppose augmented X, B, and C are augmented matrices, okay, each representing a different n by n system of linear equations. If augmented A and augmented C are row equivalent matrices, then the two systems are also equivalent. Or in layman's terms, let's go back to our differential question. What this is saying, if this is A augmented B, this matrix here, and this is C augmented D, these two are equivalent. This one here and that one. Why? Because you can row reduce it to make it look like that. Again, that's what equivalence means, right? So we just do it in general term now instead of just a simple 2 by 2. So now we have a total of n by n. So any two augmented matrices are equivalent as long as one can be manipulated to look like the other. That's what equivalency means in linear algebra. Okay.